Hello everybody, welcome. Enjoy your lunch. You can eat during the lecture. Please find a nice seat. I'm very happy you all came to the Einstein lecture by Professor Hans Hilgenkamp. Welcome also to the members of Arago, with whom we organized this lecture series together. We're already planning lectures about Tesla and Heisenberg next season. We had Newton with Fokke-Jan Dijksterhuis, and this afternoon Einstein, we can't miss in this series, of course. I'm very happy that Professor Hans Hilgenkamp is our speaker of this afternoon. He's a full professor of physics at the University of Twente. Some of you may know him from his lectures. He was the former dean of the T&W faculty. Now he's back into science again. He recently founded the Brains Center. That's a Center for Brain-Inspired Nanotechnology. It's very, very interesting. They're looking at our very highly energy-efficient brains and try to make use of that for more efficient computing hardware to realize that. So that's very interesting. Talking about brains, I think Einstein is a very brainy person. So I give the floor to Hans Hilgenkamp. Hans, hope your mic works. Yeah, and I want a big hand for Hans.
Okay. Good. Good afternoon, everybody. I hope it's working. Should I switch something here? It's on. It's on. Okay. Good afternoon. It's my pleasure to give this talk, and thank you for being here. You could have enjoyed the sunshine or learned for your exams, but it's my pleasure that you're here, and I'll do my best in the next 45 minutes to give you a glimpse of the life and work of Einstein, and maybe also with some, a bit of entertainment, scientific entertainment, I would say, because there's so much nice things you can say about Einstein. You could spend about 3 days on it. And I would like to thank therefore also Peter very much for inviting me to give this talk, because I had so much pleasure in preparing for this, learning new things about Einstein, that I really enjoyed it. So Einstein, let me just start from the start. He was born in Ulm in Germany on Pi Day, as they call it now, 3.14, Pi-dag, March 14. So he's German from origin. I'll come back to that later. He was born in a Jewish family, but not a very strict Jewish family. So they were a bit loose from the Jewish traditions and religions. But his original denomination is Jewish. After 1 year, he moved already to Munich with the family. His father was a very quiet, soft-spoken, soft, gentle person, and that's one side you see back in Einstein. His mother was a more assertive person, and that's another part you also see in Einstein. She was also the one who introduced him to music that he enjoyed very much, and they lived together with another family, his uncle, Jacob, and he was very much in mathematics, so that's the person from who he picked up the mathematics. He didn't really like it in school. He had his high school years and his elementary school years in Munich, in a time when Germany was becoming very nationalistic and militaristic, and he also felt that in school this militaristic attitude was very, very strong, and he resented this very much. He was very against this authoritarian aspect, this hierarchy, and that's very profound. His family moved to Italy when he was about 16 years old in Milan. So he finished his high school in Germany, but then moved to Milan for a short while, Pavia later on. But the family decided it was good for him to get a diploma, at least in a German university. He liked it very much in Italy, but he moved over to Aarau in Switzerland to live with some relatives. And at that time he also gave up his German passport, because he resented so much this German culture. He wanted to get rid of his German passport, so he became stateless at the age of 16. That's quite a strong thing. Maybe also related to the fact that he would have been drafted for military service, but it's quite I have children in the same age. I would be quite surprised if they would come over and say, I handed in my passport, because he became stateless at that time. Later on he got a Swiss passport, and I'll come back to this later on again. So he did his studies physical sciences at the ETH in Zurich. At that time, it was the Eidgenössisches Polytechnikum, and he enjoyed it very much in Zurich. Actually, I lived myself about here for 1.5 years when I worked in Zurich myself, and it's a wonderful place to be. He studied physics, and it was a combination of theoretical and experimental physics, but he was much more, let's say, inclined to the theoretical side. And also there, he had some difficulties with the different professors. So some of them he really admired. Some of them he felt that they were not really up to par, and that holds especially for the more experimental professors. And there's a nice anecdote of an experimental work he had to do at one point, dealing with vacuum. So this is a more modern vacuum equipment, a glass jar, as they call it, with a vacuum pump, and you can just pump the air out of the glass. And he had to do a practical assignment with this air, but the instruction was not to pump too much, because that this bell jar was not equipped for that. But Einstein wanted to test whether he could actually get the ether out of the system. So there was this notion that light travels in waves, and that there has to be a medium in which this light travels. And the idea was that this medium is something called ether, of which nobody really knew what it was, but there must be a medium in which there was this light traveling, so that could have been this ether. So he first pumped out basically all the air, but then he continued pumping until at some point this glass jar really broke, and he quite badly hurt his hand. This is the only piece of experimental work I could find of Einstein. So he was much more into the mathematics and the theoretical work. At the ETH, he also got acquainted with one of his classmates, Mileva Maric. She was a very good student, originally from Serbia, one of the very few female students studying physics at that time, the only female student in his class. He was a very diligent student, and Einstein got acquainted with her, and they fell in love, and maybe he was not really a good influence on Mileva Maric. Einstein was much more loose. He did not really do what his professors really wanted him to do. He went more his own way. And I think that also had not really the best influence on Mileva Maric. In the end, they continued in their study. Einstein did, in the end, in his own way, maybe a bit better than Mileva. And at some point, Mileva got pregnant. So she got, and they were not married, so there was a bit of a scandal. She went back to Serbia, to her hometown, and got a daughter, Lizo, in 1902, so that was when Einstein was at the age of 23. And they handed the daughter over to adoption, so probably one of the family members took care of the daughter, but and it's not really clear what happened, but the information that you can find is that she probably died of scarlet fever quite at a young age, at a few years old. Later on, they got 2 more children. In 1904, a son, Hans Albert, he became a professor in hydraulics at Berkeley University and died in 1975. And in 1909, another son, Eduard, he was into psychiatry, but he was at the same time also a psychiatric patient, so he ended up in a psychiatric foster home in Switzerland. I'll come back to Mileva Maric later on. Einstein had a pretty hard road to get his PhD accomplished in Zurich, so he finished his, what you could say, his bachelor program, but then he had to make money for his family, and he went over he applied at several places. He actually applied also in the Netherlands in 1901 already, in the lab of Kamerlingh Onnes in Leiden, but was not accepted. He started to work, and I'll come to that in the next slide, in the patent office in Bern. And at the same time, he felt it would be important still to get his PhD completed, because his vision, his dream was to work in theoretical physics at a university, and he really needed a PhD for that. So he wrote several PhD theses, but the first ones were all rejected by the professors. So the first one on thermoelectric effect. So if you apply a temperature gradient in a material, you can induce an electrical voltage. This was rejected. A PhD thesis on forces in a gas, which was rejected. And then a third attempt a few years later on moving bodies. So what happens if materials, if things move, and they call it the electrodynamics of moving bodies. What was also rejected, but which was actually the precursor of his later work on the theory of relativity, to which I'll come to in a few minutes. So then he thought I should write something more, let's say, mainstream, something that is probably quite acceptable, and he wrote a fourth PhD thesis about diffusion. It was actually about diffusion of sugar molecules in a teacup, and based on considerations about diffusion, how molecules can move in a material, he was actually able to derive equations from which you could determine the size of molecules. So depending on the speed with which molecules can diffuse in material, you can relate that to how large molecules actually are. And that was accepted in 1905. So then he was a PhD. And this thesis formed the basis for his article on Brownian motion. So Brownian motion, you may know, if you have somewhat larger particles like these pollen in a liquid, like water, and you look under the microscope, you see these pollen move, and that's because there are continuously atoms hitting these particles, but statistically sometimes a little bit more to the left and then a little bit more to the right. So these elements, they move a little bit, as is shown here as well. And at that time, they actually, nobody had ever seen an atom or a molecule under a microscope, so there was still a bit of a debate whether these things really existed. And in a sense, Einstein's work also laid the foundation for, let's say, the acceptance that there are molecules. So that's quite profound work. As I said, he had to make money, so he got a job as a patent attorney in the patent office in Bern, where they had this very modern stay tables, so that was quite good. And he combined his patent work with considerations about new concepts in physics. He had a few friends there with whom he discussed a lot about the physics, while Mileva was taking care of the kids and getting a little bit more and more away from physics, although she also had all these interests. Einstein was more the person who really enjoyed being the physicist, and Mileva was put a little bit into a position in which he had to take care of the family. In 1905 was the magic year of Einstein, what we call the annus mirabilis. So he published 4 papers in what was at that time one of the most prominent magazines, Annalen der Physik, about different topics. I have made copies of these papers. They don't look very spectacular. It's just text with a few equations. It's no figures. And some of them are really short, but they were revolutionary in physics. So this is the one about the Brownian motion. If you can speak German, you will see that it is suspendiert in Teilchen, so particles suspended in a fluid, and the motion of these particles. So that was basically his PhD thesis, but then in a publication. This was a paper about the photoelectric effect, which I'll come back to in a minute. It's what happens if you shine light on a material. And these are 2 papers about the special theory of relativity, and that I will also describe in a few minutes. So the photoelectric effect is actually the effect for which Einstein later on got the Nobel Prize. He did not get it directly for the theory of relativity or something like that, but for the photoelectric effect. And in this paper, he describes what happens if you shine light on a material, and especially what happens related to the fact that then particles, electrons, come out of the material. So this was a known effect, discovered or studied experimentally by Philip Lenard cathode ray luminescence. So when light shines on a material, there's a ray of particles coming out, electric particles, electrons. And some things were known in advance. So what was known already from the previous century was that the energy of light wave was in a way connected with the frequency or with the wavelength. The bluer the light, the more energetic the light was. This was already something that was known. Another thing that was known was by Max Planck, that in a material we're dealing with discrete particles, atoms, things that you can count, discrete things, and also exchanges of energy with material was in a way quantized. This was going in packages of energy. That was found out by Max Planck, but light was considered to be something continuous. This was a wave, as I said before. The medium was not completely clear, but it was a kind of continuous thing, not quantized at all. What Einstein discussed was that if this is a continuous medium, if you would shine more intense light, so if you increase the amplitude a little bit of the light, you would expect these electrons to move faster. Just more energy would be transferred to these electrons and they would move faster and faster. But what happened in practice was that if you increase the intensity of the light, the electrons would not be faster, but there would be more electrons. And this was the consideration by Einstein, that this energy transfer has to go in packages. There is a package of light coming in. Somehow it interacts with the material. It ejects an electron. And that's then the process. And if you have more intense light, you have more packages of this energy. So in the end, you have more of these electrons coming out, rather than that there is a big splash and very fast electrons come out. That was the basic notion by Einstein, from which he derived that light also had to be not continuous, but going into packages of energy, and which were later on called photons. So this is the paper. As I said, they don't look very spectacular. This is maybe the most important paragraph. I will not read it all in view of the time, but it says something like, really it looks to me that if you look at the black body radiation, that the energy of the light has to be discontinuous in space, so that there are packages of energy in light. So this was the basis for understanding that light not only is a wave, but also is composed of particles. And in a sense, this also is then the first real, that's a paper describing what we now call in quantum physics the particle-wave duality. Things like light, and also later on it was found out that the real particles, sometimes they have a wave character, and sometimes they have the character of a particle, depending a little bit on what you are measuring. And the paper shows that light is not only a wave, but also a particle. In that sense, he also discovered then the photon. Then there was the other aspect, the relativity. Let me first introduce a little bit classical relativity. So if you are in a train with 50 kilometers per hour, and there's another train approaching with also 50 kilometers an hour, and you just look out of the window, you will see this train pass by with 100 kilometers per hour. And sometimes you don't even know, you all recognize this from the stations, you don't really know where you're moving yourself or the other one is moving, but you see this thing passing by with 100 kilometers per hour. That's classical relativity. Also the people in the other train will see you pass by with 100 kilometers per hour. This is completely in line with everything that was known from the time of Galilei and Newton. What makes it now special is what Einstein said, that if you look into the speed of light, that if you're in this train, you will see this light beam approaching to you with the speed of light, and this is a constant. And this holds for all observers. So if you're in this train with 50 kilometers per hour in this direction, or if you're standing still, or if you're going with 50 kilometers in the other direction, it's always the same. You always see light moving with the speed of light, and this is a constant value. Later on they found out it's 300,000 kilometers per second. Or actually they knew that the speed of light was already found out, but Einstein said the speed of light is constant for all observers, and that also means that all the laws of physics related to the speed of light are also equal for all observers. This has quite profound consequences, but consider you're in a rocket traveling with 299,000 kilometers per second towards a light beam. You would say, okay, well, this astronaut sees the light coming in with about 1,000 kilometers per second. That's not true. Also in this rocket, people just see this light coming towards them at 300,000 kilometers per second. Just the same as when you're standing here, you see this rocket flying by this direction, you see the light coming from that direction. Your idea of the speed of light is exactly the same as for the people in the rocket. It's quite strange if you think about it, because it just, it has some strange consequences. One consequence, for example, is that your whole idea of time is different if you're just standing here or if you're sitting in the rocket. You can do the mathematics, and there is an expression for this. So compared to our time, t, this is just our natural time here. For the people in the rocket, time goes with this expression. So this is their speed, 299,000 kilometers per second. This is the speed of light. And this you can just shorten down with this expression if g is this expression. And that means that the time in the rocket for our consideration is different from the time that as we notice it, and the difference is this factor g. Now g is 1 if you're talking about very small velocities, then this is negligible and this becomes 1. So if you're at very small velocities, nothing really happens, but if you're at very high velocities, close to this speed of light, it becomes really important. For example, in this rocket, if you calculate this, g is about 12, so we would say for the people in this rocket, time goes about 12 times slower than for us. The clock goes 12 times slower than for us. It's very strange, but it's a direct consequence of this special theory of relativity. And actually, this you can measure this. This really happens. One very nice example is the decay of elementary particles. If you have cosmic rays coming in, here is some kind of particle coming in the atmosphere, and it collides with molecules in the air, and there's a whole shower of particles being generated. And one of these particles, after a few collisions here and the creation of pions, etc., one of these particles is the muon. And these muons are typically generated high up in the atmosphere, and they reach the Earth. And you can measure them here on Earth. But muons have a very short lifetime. You can also do experiments here on Earth with muons that are standing still, and you can see that typically a muon decays within a few microseconds into an electron and 2 neutrinos. But they are generated at 10 kilometers altitude, and they travel with a very high speed, so let's say close to the speed of light. So in 2 microseconds, with velocities almost the speed of light, you can reach about 1 kilometer. So within a kilometer, all these muons should actually have decayed already, and you cannot reach the Earth. But because they are going so fast, the time inside the muon, if it would have a clock, goes about 10 to 15 times slower. So the muon thinks, I'm still alive. I don't have to decay yet. And in the meantime, the muon already reaches the Earth, and it has passed this 10 kilometers. It's very strange. So time is dependent on the velocity with which you are traveling. And that's the essence of the special theory of relativity. So you can think about all kinds of strange things. So if you're going in this rocket, you would say, well, this rocket is really arriving at a very high speed, almost 600,000 kilometers per second. Not true. Here you see this rocket approaching with almost the speed of light, even if you're traveling yourself also with the speed of light. This is the highest velocity possible, the speed of light. from this paper that he published, he actually wrote a second paper, very short one, 3 pages, in which he said, okay, let's take some kind of body, something that can emit light, 2 light pulses, one in one direction, one in the other direction, and let's look at it in 2 different coordinate systems, one in a coordinate system that is standing still, and the other in a coordinate system that is moving with a constant velocity. And let's look at aspects of energy and velocity. And he does a little bit of algebra, so here's one equation, this is page 2, some more equations, and quite quickly he comes to the end of his paper, and he says, well, if you just compare the energies in these different coordinate systems and the velocities, and you do a little bit of mathematics, you have to conclude that if a particle gives away a certain amount of energy, which he calls L, in the form of radiation, then its mass will reduce by L over v squared. And v, the big capital V, is the speed of light in his story. So he makes a connection now with the mass of the particle, because the kinetic energy has a mass term, half mv squared. And he comes to a quite interesting conclusion, that there is a relation between the energy and the mass. So he says L equals, so m, or the delta m, the change of m, equals L over v squared. And this has become known as the famous Einstein equation, E equals mc squared, with L the same as E, that's the energy, and this v, the speed of light, which we know as c. So it's a kind of common knowledge that Einstein published E is mc squared in 1905 in one of his famous papers. And this is not true. There's no E is mc squared in this paper. It's m is L divided by v squared. So quite remarkable that Einstein did not propose E is mc squared originally, but something completely different. But it's now one of his most famous equations. You can also derive this if you look at the, I'll do this quickly because in view of time, for the physics enthusiasts, you can also introduce the momentum, the impulse, m times v, and the relativistic momentum, where you have to take this Lorentz factor, this one, into account. And then you find that the mass actually becomes larger when you reach the speed of light. So a particle or something that you accelerate has more and more energy when reaching the speed of light, and at the same time acquires more and more mass. So when you're very close to the speed of light, your mass has become almost infinite, and your energy has also become infinite. So that's why in a particle accelerator, like in CERN, they want to accelerate small particles, protons, to almost the speed of light, and it costs more and more energy to reach the speed of light. So now they are at 0.99999, so 8 nines, close to the speed of light. But it costs a lot of energy to accelerate particles like that. Now, how about E as mc squared? So later on, in the next years, 1906, 1907, people started to talk about this, and they used these other symbols for the speed of light and the energy. And then also Einstein himself started to talk about E is mc squared. And I hope this works. And you have to listen carefully because it's a very old recording, which is very noisy. But here he says E is mc squared.
E is equal mc squared, in which energy is put equal to mass multiplied with the square of the velocity of light, showed that very small amount of mass may be converted into a very large amount of energy.
Okay, so a very small amount of mass can be converted to a very large amount of energy, and that comes back later on in a view of the atomic bomb. Now let's move a little bit on. I have to see that I really have to speed on. So initially, this paper was not very much picked up, 1905. Only a little bit later on, when Planck started to talk about it, then it got really the credibility. Remember, he was just a patent attorney who failed his PhD exam 3 times, so he didn't have a lot of status at that time. But when Planck picked it up, he was a big guy. Einstein really got stature. Actually, it's so much that already in 1909 he got an honorary doctorate. So that's very, very quick from the University of Geneva. And in 1911, Einstein was invited to join in the first Solvay conference with many big names. Here is this was Nernst. Where was Planck? Here, Lorentz was the big scientist of that time, and Marie Curie is here as well. So he really became famous, and his theories became more and more accepted, at least in certain circles. In the meantime, he got a position as a kind of tenure tracker at the ETH in Zurich, but he got an offer for a full-term professorship in Prague. So 1911, 1912 he went to Prague. Mileva Maric joined him with the kids, but it was not really a pleasant move for her, because she really liked Zurich much more than Prague. And also Einstein was a bit isolated in Prague. He went often to this coffee house where he met with people like Kafka, but scientifically he wanted to move back to Zurich. So in 1912 he went back to the University of Zurich, one of the other universities, where he got a position. But then he got an offer by Max Planck and Walter Nernst for a very nice position at the academy in Berlin, Prussian Academy. And it was very nice for him because he had a lot of resources and good scientists around him, and not a lot of teaching duties. Einstein didn't like teaching very much. So he took that position, and he automatically became a German again. He didn't really notice it, but one of the conditions for moving to this institute in Berlin was that you would have the German nationality. So he got a German passport again. At the time when the First World War started, and there was quite a lot of discussion, of course, in Germany also about the war. Einstein already there first indicated his negative sentiments towards the nationalistic movements at that time of Germany, especially when they started to invade Belgium. In those days, Einstein extended his theory of special relativity, which was only valid for bodies moving with constant speed with respect to each other. He wanted to include accelerations, he wanted to include gravity, forces between particles, and this was very complicated. So he was working on it and realized that you needed very complicated mathematics for this. And he got the help of mathematicians like Hilbert and Minkowski, who were able to do all the mathematics. And in 1905, Einstein was able to really complete his story, including accelerations and gravity. And this was written out in 10 coupled differential equations that you can write in a shorter form in this way with tensor equations. I will not go through them. It's rather complex, but the conclusion is that you have to look at space and time as a continuum, as a continuous thing. It's all connected with each other, and space is not necessarily straight, but space becomes curved near big masses. So if you have somewhere mass with high gravity, then you can look at space as a curved object, and light beams, for example, they move in curves around such a big mass. So if you're here on Earth, you would think that this star was here, but it's actually behind this mass, and it has curved around it. Also, these dimples here in space-time can become waves. For example, if you have two masses moving around each other, it emits waves, gravitational waves, and these are the gravitational waves that were detected about 2 or 3 years ago for the first time. So this is a direct consequence of the theory of general relativity, connecting then space and time and mass all with each other. Also here, there is this aspect of what we call this time dilation, that if you are in a very strong gravitational field, if you would fly with a rocket here through this gravitational field, that your time is also different from the time as we would say here on Earth. In the meantime, he got divorced from Mileva. Mileva did not want to join to Berlin. She stayed in Zurich with the kids, with the boys. Einstein went to Berlin and later on married his niece, or his cousin, Elsa Löwenthal. She was very happy to be in the role of kind of managing director of Einstein, much more than Mileva did. And they lived happily together until Elsa Löwenthal died halfway in the 30s. At that time, we are now after the war. There was a big anti-Jewish sentiment in Germany, and this also related to Einstein. Einstein was originally Jewish, and the anti-Jewish sentiments were also connected then with this theory. So some people said that this theory of relativity was a Jewish science and that it could not be acceptable. And some of the strong people were Weiland and Geerde, and they organized meetings like this. So a series of lectures of German physical scientists against Einstein's general theory of relativity. It was very aggressive. Einstein actually went to this meeting himself. He really enjoyed the discussions, but it became more and more serious, this threat, especially after Rathenau, one of his friends, was killed in the early 20s. He was a minister in the Weimar Republic. So this anti-Jewish sentiments became stronger and stronger, and Einstein had more and more problems and difficulties with this. On the other hand, appreciation in the scientific world slowly also increased. Not so easy, actually. The Nobel Prize Committee was also a bit reluctant in awarding Einstein the Nobel Prize. They were not really sure whether they could believe this theory of relativity. At the same time, many scientists said, well, it's really about time that Einstein gets the Nobel Prize. In 1921, they had him on the list, but in the end, they said, well, maybe not. So 21, the Nobel Prize was not awarded, and then scientists like Max Planck and others advocated more and more for Einstein. So then in 1922, actually the 1921 Nobel Prize was awarded in retrospect, and then the 1922 Nobel Prize was given to Niels Bohr. And so also there you see it could have been better. And it was not really for all his work or for the most important work, this theory of relativity, but for the discovery of the law of the photoelectric effect. That was in the quotation, the thing that was mentioned particularly, and for services to theoretical physics. He became also a visiting professor in Leiden, where he was well acquainted with Paul Ehrenfest. This is the son of Paul Ehrenfest, and he really enjoyed being there. Here he is at the occasion that Queen Wilhelmina got the honorary doctorate in 1925. And there is somewhere information that he once was in Enschede, that he had a friend at the Prinsenstraat, somewhere in the center, but there's not a lot of information you can find about that. Let me skip this because in view of time, although it's really funny, but I can talk about this later on. It's about Bose-Einstein condensation and particles that are either social or asocial. But I want to go to another part. And so he has done a lot of work. As I said, I could spend 3 days talking about Einstein, and certainly Bose-Einstein condensation is very important. He was one of the most influential scientists of his time. Now you see the 27 Solvay conference. He's sitting in the center next to still Lorentz, which was really one of the eminent scientists in this whole period. Does anybody recognize who this is? Yeah, good, very good. So at the end of the 20s, he started to become connected with Caltech, and he did kind of winter breaks at Caltech. He also wanted to escape a little bit from Germany. So he went to Los Angeles, Pasadena, where Caltech is, and he got well connected with Charlie Chaplin and some other people at that time. And at that time, there was also an ongoing discussion about new developments in quantum physics. There was a so-called Copenhagen school, new people, Born, Heisenberg, Schrödinger, developing new concepts in quantum physics. And this was something that Einstein really had difficulties with. The essential thing about quantum physics is probability. So there is a certain chance probability that an electron is here or here. And only if you measure it, you know for sure whether it's here or here. But there is a certain chance, a probability function. And Einstein had difficulties with this probability aspect. One of the famous quotes was that God does not play dice. So this whole concept of chance and probability is something that he did not like. He said there has to be something behind it that is really controlling everything, that makes it deterministic, so that there's no room for something that is fuzzy and has a chance. And he was in a discussion about that with the people developing these new concepts in quantum physics. And in that sense, he became a bit the old man, having difficulties with the younger generation, while he himself was, when he was a young person, he completely overthrew the whole classical physics. Another famous expression is about entanglement, that you can have two particles at different positions still together in one quantum mechanical state. That's called entanglement, and that if you would measure the properties of one particle, you immediately fix actually also the properties of the other particle. That's a bit the essence of quantum entanglement, from which quantum teleportation is also derived. And he called it a spooky action at a distance, spookhafte Fernwirkungen. Later on, this was actually measured. There were the so-called Bell tests were done in optics by Alain Aspect. Quantum entanglement was very nicely demonstrated by Zeilinger. And very recently, a few years ago, the group of Ronald Hansson in Delft made also very, let's say, definite measurements showing that this entanglement really exists. So he is really a strong candidate for a Nobel Prize. Zeilinger as well, and I would not count out that Ronald Hansson could be included in this list, but who knows. There was a talk about Newton. You have a few minutes, so let's wrap it up. By Vanco Jan Dijkshuis a few weeks ago. So let's make a few comparisons between Newton and Einstein. There are some similarities. Both were really focusing on very fundamental things of nature: forces, energy, mass, light, the very profound things of nature. What is really striking is that both made their most important work outside a university. So this may be for Vision 2030, maybe an interesting aspect, that Newton was away because there was the plague in Cambridge. He was at home. And Einstein was in the patent office, so they were not directly at the university when they did their most important things. Let it be a lesson. They were both excellent mathematicians. They actually also, Newton already had considerations of light as particles, which were later a bit discarded, but he was also on that track. And also they had major societal and political influence in their later careers. Newton was also very influential. But there are some differences, of course, in the physics, and Newton with the velocities adding up, Einstein with the relativity, space is straight and fixed, space is curved and dynamic, no maximal velocity, the speed of light. Newton was much more localized, he never left the area around Cambridge and London. Einstein was very international. Newton was also a good experimenter. Einstein gave it up after his vacuum experiment. And Newton was really very exhaustively mathematical. And Einstein used a lot of Gedanken experiments, so thought experiments. And so then, when Hitler got the power in Germany, he really moved definitely to the US. He was first wanted to go to Caltech, but that didn't really work out, so he ended up in Princeton, in the Institute of Advanced Studies, where Robert Dijkgraaf is now the director. And he continued working, trying to combine this general relativity with the new quantum physics theory, but also became more and more connected with world peace and aspects of that. So he, when the war approached, he realized, together with some other scientists, that there was a big danger that Germany could develop a nuclear bomb. This whole ESMC squared had been worked out further on, and people realized that you could make very powerful weapons if you can convert mass into energy, because of this c squared, this very high term. So people learned more and more about nuclear material, and that you could possibly make a bomb with nuclear material. And the most important source for nuclear material was in Congo, uranium, and Belgium was Congo was a colony of Belgium. So Einstein, together with some other people, wrote a letter to Roosevelt, who was president of the US, asking the king of Belgium to make sure that Germany would not get uranium, and so they did. But at the same time, the Americans realized that, well, maybe it would be a good idea to make their own atomic bomb. So that really was the start of the Manhattan Project. Einstein was not invited to join the Manhattan Project because he was considered to be too much of a risk because of his pacifist ideas. And actually, later on in the files, they found out that one of the people that organized this original anti-Einstein meeting, this Weiland, that he informed the FBI or the CIA that Einstein was a communist, or so they found out in the records that he was behind it, which prevented Einstein from joining this Manhattan Project of making the atomic bomb, which I think he would have really resented anyhow. But he became very active in promoting pacifism, and I also have a nice little video quote about that. It's also difficult to hear, but he basically says we have to watch out that the US and the USSR, so Russia, do not embark on a path of increased weapons, making weapons and making use of this strong force of nature. So let's see if we can hear it.
Is there any way out of this impasse created by man himself? All of us, and particularly those who are responsible for the attitude of the US and the USSR, should realize that we may have vanquished an external enemy, but have been incapable of getting rid of the mentality created by war. It is impossible to achieve peace as long as every single action is taken with a possible future conflict in view.
So he basically says we have to really watch out that there's no future war, because we have created now so strong weapons that this really becomes a big risk. I have 2 or 3 more slides and then I'm at the end. He was also very connected with Weizmann, who was influential in forming the state of Israel. So the Jewish population embraced him as a Jewish hero, and he also really felt very positively about creation of the state of Israel, but then in a very good blending with the Palestinians. He had the idea of just a state there where the Jewish and the Palestinian communities would live together. When Weizmann died in 1952, Einstein was asked by Ben Gurion, who was the prime minister of Israel, to become the president of Israel. But Einstein declined. He said, I'm not so good in working with people and all this politics. I'm better in science, so I'll better not do this. But he could have become the president of Israel in 1952, and you can wonder what would have happened then in the development of Israel. He got a lot of prizes, starting with his honorary doctorate in Geneva and the Nobel Prize. This is nice to mention the Max Planck medal, because one of our colleagues, Detlef Lohse, just last month also got the Max Planck medal from the German Physical Society. It's a very high honor. Honorary doctorate from the ETH Zurich, where he first did not manage his first 3 attempts to get a normal doctorate. This one is nice, de genootschapsmedaille van het Genootschap ter Bevordering van de Natuurgenees en Heilkunde. This is the only Dutch award that he got, which he really picked up himself. So in the end, he was a highly honored scientist. Einstein died in 1955. He had an aneurysma that broke, and this was world news because he really was a famous person. And at the end of the century, he was, by Time magazine, called the person of the century, so most important. So even after, surpassing people like Hitler, there was a physicist called the person of the century, which I think is a nice tribute to our field of science and, of course, to Albert Einstein himself. So that brings me to the end of my talk. If you want to know more about Einstein, you could also go to a talk tomorrow evening. There will be a talk in the Wire by this person about Einstein, maybe more going into some of the physics aspects, but I would leave it with this. Thank you very much.
Thank you. Hans, thank you very much. You did a tremendous job explaining Einstein's life and work almost at the speed of light, because it's such a complicated life, so many theories. Thank you very much. I want to read one quote of Einstein. If you can't explain it simply, you don't understand it well enough. Well, this doesn't apply to you, because you explained everything very, very good. You understand it very well. You explained the theory of relativity with the ice creams approaching each other, the muon decay, which was very interesting, and I had never realized it, that they live long enough to reach the Earth because of special relativity. ESMC squared, you explained where it came from, so it was a great job you did. Thank you very much. And this summer, when you're eating ice cream, when you're licking on your rocket, please remember the theory of special relativity. Hans, thank you once more.
Thank you.
Thank you. And perhaps for the fijnproevers, for the what's it called in English? The
Tasters.
Fine tasters. Thank you. The fine tasters. Maybe you can explain. You can leave if you have to go to lectures or whatever. But we round off. The Bose-Einstein Condensate slide you had with the huishoudtrapje. I'm sorry about my English.
Yes.
Yeah.
Okay.
So if people want to know, please come to Hans and he can explain it. Thank you once more and see you next time. Big hug.